This is a benzene and its compound tutorial presented by the SHLTP with reference Cambridge International AS A-Level Chemistry by Laurie Ryan and Roger Norris. So we start with the learning outcome. So you should be able of benzene and its compound. You should be able to interpret, name, use the general structural display skeletal formulae of benzene and simple aryl compounds. Describe and explain the shape, bond angles in benzene molecule. We have described the reaction of aryls with benzene, such as benzene and methyl benzene, substitution reactions, nitration, Friedel Crafts, complete oxidation. We have hydrogenation. Describe the mechanism of electrophilic substitution in arenes. We have interpret the difference in reactivity between benzene and chlorobenzene. Predict whether halogenation will occur in side chains of benzene ring in arenes depending on reaction. We have applied the knowledge of relating to position substitution and all that. So now let's start with benzene and its compounds. So we first need to point out what is benzene ring. So now the benzene ring is actually having this formula. This structure here is named as the Kekule structure of benzene. Now the Kekule structure of benzene says that there can be rotation. So since these electrons are delocalized, you can have this double bond at this position here, this double bond at this position here, and this double bond at this position here. So that those are the Kekule structure, and those Kekule structure are the resonating forms of benzene. What is resonance? What is resonance? Resonance is the ability of a compound having the same molecular formula but different with the convention. There's a conventional difference in the main structural formula of this compound. None of the structural formula that is drawn of this compound is going to account for the physical properties of this compound. So that is what is called resonance. And the different structures of this compound are the resonating structures. So as you can see here, this is a Kekule structure. So now let's continue. So the benzene ring is a C6H6 molecule, as you can see here. And now this Kekule structure, now since you have different Kekule structure and we have resonance existing, which does not really account for the real formula of benzene, because the Kekule structures here shows that it has a double bond, but actually benzene is not capable of decolorizing bromine water as in cases of alkenes. This is why it's another structure that we usually draw for benzene, and this is the structure. This structure contains delocalized electrons. It does not really say that benzene has double bonds. It just says that the electrons are moving all through the space of benzene. So now this single bond, carbon to carbon single bond, has 0.154 the bond length. Carbon to carbon double bond is 0.134, but carbon to carbon bond in benzene is actually 0.139. So we see that actually these bonds do not exist in benzene itself, but in the formula of benzene they actually do. This is why, since this bond length actually in benzene is different from this Kekule structure, we can now say that this Kekule structure is not the actual structure of benzene but a resonating structure. So benzene has a structure to itself which is not accounted by its structural formula given by Kekule structures. So this structural formula like that is this one. So that's why most of the time you're going to see the diagram of benzene being drawn as such. So now we need to know that benzene have delocalized electron. As you can see, since they are delocalized electron, these delocalized electron are going to do bonding by pi bonding. The first bonds here are going to be sigma bonding, and now those since there are py orbitals which are being left here, those py orbitals are going to bond to each other with the pi bonding. And the pi bonding, we know that pi bonds are bonding that where electrons are far away from the bonding nuclei compared to a sigma bond. That's why pi bonds are less stable compared to sigma bonds. So now let's continue now with the naming of aryl compound. When you want to name aryl compound, just need to know that this is position 1, position 2, position 3. So this is position 1 here, this is position 2, this is position 3, position 4, position 5, and position 6 of benzene. The molecule which is found on position 1 is the molecule that is controlling the naming of the benzene. So at position 1 you only call it chlorobenzene. Here you call it, since at position 1 you call it nitrobenzene. At position 1 you call it phenol. At position 1 you have one molecule at position 1. This molecule is going to account for the main name of this aryl compound. So this is already phenol, as you have seen here. But now you see that there is position 2, there is position 4, and there is position 6. All there are bromine molecules there. So you are going to call it 2,4,6 tribromo phenol. Then you have here position 1 here, you are going to call this molecule phenylamine. So now the next one are the reactions of bromine. We need to know that the main reaction of bromine is going to be electrophilic substitution reaction. In electrophilic substitution reaction, we have initially told you that bromine is going to contain delocalized electrons. So bromine, I've initially told you that benzene is going to contain delocalized electron. So since benzene contains delocalized electron, it is electron rich. So the type of reaction that, since this electron rich center, since benzene is an electron receptor, the type of reaction that is going to occur is an electrophilic substitution reaction. There can also be electrophilic addition reaction, like in the case where you have a hydrogenation of the benzene ring, like in the case where you have hydrogenation of the benzene ring. But now, in case of electrophilic substitution reaction, this is not hydration. So here, for electrophilic substitution reaction to occur, what needs to be there is that you need to produce a positive ion. So an electrophile, and an electrophile is going to contain a positive ion. That electrophile now is going to enter into the ring, and it's going to be written as such. So example, we have benzene ring plus bromine in presence of iron tribromide. So iron tribromide, as you can see here, so, or iron tribromide. So when you have this, you are going to have this equation. So now let's see the mechanism of this to occur. So now this mechanism, you see that what iron tribromide, which is the catalyst of this reaction, is going to first pull one bromine from this bromine molecule. So now when it pulls, it produces one positive bromide ion and the other ion. So this is the tetrabromoferrate 4. So you need to calculate the in order to have the name of this molecule, you need to calculate the number of the oxidation state of iron. So tetrabromoferrate 2. So this is tetrabromoferrate 2. Now when you have this, you now put a negative ion. So this is the ion here. So now the bromine, now you see that when you draw this curly arrows, this curly arrow shows that electron move from, it shows the direction of electron motion. So you see that electron is going to move from the benzene ring into this bromide positive ion. So this shows an electrophilic substitution reaction. So now we have stage 1. Now you are going to have these two molecules here. See that the electrons from the hydrogen, since hydrogen is also bonded to this position, electron from the hydrogen is going to enter into the center, and then stage 2, you see that it's going to break down, and then it's going to produce this. So now the hydrogen now is going to bind again with the other bromide ion negative, which was here, to form hydrogen bromide plus this catalyst which was found there. So that's the point. The next point is also in the formation when you want to use, instead when you want to let's say do the chlorination of the benzene ring, we need to know that what the methyl ring is used in the activation of the benzene ring. We need to know that what methyl ring, we have molecules that can activate the benzene ring, and we have other molecules that can deactivate the benzene ring. So let's take example. We need to know that what the methyl group or an alkyl group is going to activate the benzene ring. Now the second point is, let's see this formula here. You need to know that the OH group is also activating the benzene ring. We have the even the bromide group, the alkaline group, the halide group also activate the benzene ring. The amine group is going to activate the benzene ring. This amine group is going to activate the benzene group. The only one that does not activate the benzene group here is the nitro group. The nitro group is going to deactivate the benzene ring. And now, what is the significance of activation and deactivation of benzene ring? A molecule that activates the benzene ring is going to cause later electrophilic substitution to be on the para or the ortho position. What do I mean by that? The molecule is the addition of another, the electrophilic substitution is going to occur at this position 2 here, which is called also the para position, or it's going to be at position 4 here, which is called the ortho position. Why in the case of a nitro group, which is causing a deactivation of benzene ring, you instead have their electrophilic substitution is going to be taking on this place on the ortho position, on the meta position here, and the meta position is position 3. So on this meta position. So now let's visualize now in this case. In this case, you see that the methyl group is going to be an activation. Is going to activate the benzene. See, activate the benzene, the chloride, the chlorine in presence of aluminium trichloride. Chlorine is going to add up to the para position, that is position 2, or the ortho position of position 4. So it's going to form 2 chloromethylbenzene or 4 chloromethylbenzene. These are the two molecules that are going to be formed. So now the next one is alkylation or acylation of the benzene ring. Alkylation is the addition of an alkyl group, while acylation is addition of an acyl group. An acyl group is an alkyl group plus a carbonyl functional group. So now let's visualize this. A Friedel-Crafts reaction is just this alkylation or acylation of the benzene ring. It's electrophilic substitution in order to increase the number of side chains in the benzene ring. So how is it occurring? So you do an alkylation. This is an alkylation. An alkylation you use any haloalkane. You use any haloalkane. Now when you use alkyl, you place aluminium trichloride like this one. This is chloroethane. Chloroethane and aluminium trichloride. When you place it, you are going to form now you are going to put this side chain, the ethyl side chain, on this molecule. So you are going to let's see, you are going to see the mechanism later. So you are going to form now ethyl benzene plus hydrochloric acid. And in case of acylation, you can use ethanol. You can use any acid chloride, as you are going to see in the next chapter. You are going to use aluminum trichloride as being the catalyst. You are going to form this molecule. So now let's visualize the mechanism. For the mechanism, we need to know that what the first thing, the aluminum trichloride is going to pick up, a chlorine is going to pick up and then add up to aluminum trichloride to form this and this electrophile. Now this electrophile is going to take electron from the benzene ring to form this, and now the hydrogen is going to lose electron and then form back the benzene, the aryl group as such here. So this is the final formula, and this is similar for this molecule. For this molecule, you instead have CH3CO positive that is going to be formed, and the positive on the C now is going to add up to the benzene ring. So now we have oxidation of the side chain. We need to point out the fact that the benzene ring increases the oxidation power of the side chain. The benzene ring increases the reducing power instead, because when this benzene ring with this aryl compound here is going to be much more reducing compared to only an alkane. So this aryl compound here is much more reducing compared to an alkane. Normally, when you oxidize, you are not capable of oxidizing an alkyl group. But now, when you have a benzene ring attached to that alkyl group, the reducing power of this molecule is going to increase. Since the reducing power of this molecule increases because of excess electron found in itself, we are going to find that since it increases, it's going to be highly oxidized. The reducing power of this molecule is increased, so the molecule is going to be highly oxidized to produce now this COOH group. So if you use here acidified potassium permanganate can convert all through to form this molecule, this acid here. So now these are the different things to visualize here. Now we have phenol. For phenol, we need to know that phenol is compared to the other alkyl group, phenol has a higher melting point, and the question is why. This is because of the hydrogen bonding that phenol has. So now the next point is you need to know that phenol can exist both as an acid or as a base. So now let's see in case of acid. So you need to know that the phenol can push electron from the hydrogen, as you can see here. Phenol can push electron, oxygen can, since oxygen is more electronegative, it's going to push electron from hydrogen and break the bond between the OH, and you can form the phenoxide ion. This phenoxide ion now is now capable of binding to other molecules. So you have ethoxide ion and all that. So this is the ethoxide ion found in cases of alcohol. This is phenoxide ion found in case of phenol. So now let's see the reactions of phenol. You can have reaction with sodium hydroxide to produce sodium phenoxide plus water. You can have reaction with sodium to produce sodium phenoxide plus hydrogen. Now substitution into benzene ring of the phenol. So you have also substitution into benzene ring of phenol. So now this is a phenol molecule. We have initially told you that the OH in the phenol molecule is going to cause an activation, while the Br, the bromine, is instead going to cause this bromine also causes an activation. So now since in this case you see that what this is the molecule that is going to be found at the end of the reaction when you bind phenol to 3-bromide. But the question I want to ask you is, realize that bromine is activatory while phenol is also activatory. So when you have first this phenol and the first bromine molecule is going to add up, you see that since bromine is activatory, the next molecule for bromine has to come at this position and at this position. Are you seeing? So now since it is not instead coming at this position, you can conclude that phenol is much more, has a higher activatory effect than bromine. So the equation, the final formula is going to respect the order of phenol. So now let's visualize this other one. When you add now phenol with dilute nitric acid plus sulfuric acid at temperature of 55 degrees Celsius, you are going to form now this ion NO2 plus. So that's the ion that is going to be found, and this ion now is now going to be electrophilic and bind either to this position or this to this position. So this is why, since it binds to this position, you can now think that phenol is actually activatory. And also you are also capable of finding this one, trinitrophenol. So trinitrophenol now is capable of easily be formed, because when this first nitro group come at this position, what do you realize? You realize that when this first nitro group comes at this position, the first thing that occurs is that this one is deactivatory. Since deactivatory, the next molecule needs to come at the meta position with respect to the nitro group. So it is easy to form this molecule compared to this other one. So here there is going to be an opposite effect for the formation of this molecule, and here there is an the summation effect for the formation of this molecule. So from here we have visualized everything involved with the benzene ring. I will say thanks for your kind attention. Please don't forget to like and subscribe the channel. Thank you.